The next several sets of videos introduce us to the Laplace transform and then show us how it is used in solving differential equations. First, I'm going to start by defining a transform, and it's a terrible definition, but it transforms one function to another function. You've seen transforms before because the derivative and the integral are both transforms. For instance, the derivative of the inverse tangent of x is 1 over 1 plus x squared, so that inverse tangent got transformed. The integral of 1 over x dx is the natural log of the absolute value of x plus c, and again, 1 over x has been transformed to that natural log. There are two properties in math known as linearity properties, and one of them says that essentially something respects a sum, and another says that it respects a constant multiple. The example we're looking at here is that the derivative of a sum of functions is the sum of the derivatives of the functions, and a constant multiple inside of a derivative can be moved outside of the derivative without affecting the result. When you differentiate and integrate, you use these two properties all the time without even thinking about it, and they apply to the Laplace transform as well. What is the Laplace transform, you ask? Well, the Laplace transform of a function f of t is equal to an integral from 0 to infinity of e to the negative st times f of t dt. In this expression here, the thing inside the curly braces, like the notation is sometimes a scripty L, sometimes a regular L, but it's a scripty L, curly braces f of t. The thing inside the curly braces is the thing that's being transformed. And that's the function f of t that we see in the integral. The e to the negative st is part of the definition of the Laplace transform. Another part of the definition is that this integral is the transform of f provided that the integral converges. Because the Laplace transform is an integral, it possesses the same linearity properties that an integral possesses. It's a little bit difficult to talk about the integral that defines the Laplace transform without seeing it in action. So we'll see a few examples and then we can explore it more as we go. We're going to look at the Laplace transform of 1. So now 1 is the function that we're going to put inside the integral. So the Laplace transform of 1 is equal to the integral from 0 to infinity of e to the negative st times 1 dt. Now, ordinarily here, you see things like this is the limit as maybe b approaches infinity of the integral from 0 to b, blah, blah, blah. I'm not going to bother with any of that for anything in this chapter. Now, to integrate e to the negative st, I think about what I would do if I differentiated it. I would multiply by negative s using the chain rule, right? So to integrate it, I'm going to divide by negative s. We have e to the negative st, and that's evaluated from 0 to infinity. The negative in front of the s in the st exponent puts that term in the denominator. When we put infinity in place of that t in the denominator, the result is going to be 0. When we put 0 in place of t in the denominator, that gives us a factor of 1. And since we're subtracting the lower limit evaluation, the answer turns out to be 1 over s. We're going to develop a library of Laplace transforms. So here, this is the first entry in our library. Let's look at a more interesting example. We're going to evaluate the Laplace transform of t. That means we're going to set up an integral from 0 to infinity, e to the negative st times t dt, right? Because whatever the curly braces are holding, that's the function that we're transforming. This requires integration by parts. I'll say that u is t, so that du is dt, and dv is e to the negative st dt, so that v is negative 1 over s e to the negative st. Then using the integration by parts formula, we have negative t over s e to the negative st, and that's evaluated from 0 to infinity. Minus gives us plus, for the integration by parts formula, the integral from 0 to infinity of 1 over s e to the negative st dt. You'll note that as t goes to infinity, the e to the negative st, that's a factor in the denominator again, is going to outpace the t in the numerator. If you wanted to use L'Hopital's rule, you could see that that limit would be 0. Putting 0 in place of t is going to zero out that term entirely. So the first term here evaluates to 0. For the second term here, we're going to integrate 1 over s e to the negative st with respect to t. We get negative 1 over s squared. I'll put the e to the st in the denominator this time, and we're going to evaluate from 0 to infinity. Again, we have e to the infinity in the denominator for the upper limit, and then we're going to subtract off the evaluation at the lower limit, and the result is that we have 1 over s squared. And now I can kind of talk about something here. The Laplace transform of t is equal to 1 over s squared. This wasn't obvious in the previous one because we transformed the constant function 1, but generally speaking, in this whole chapter, our independent variable is going to be t. And when we apply the Laplace transform to a function of t, because we're integrating with respect to t and then substituting, and because of the s in the definition, our answers are going to be functions of s. This is a good visual distinguisher. When I see a t, I know that's pre-transform. And when I see an s, I know that that's a function that has been transformed. I'll come back to that thought as we put things together through this set of videos, but keep that in mind here. Now we're going to use the linearity of the Laplace transform. We have the Laplace transform of 4t minus 7. This is going to be the Laplace, I'll really drag this out here. The Laplace transform of 4t plus the Laplace transform of negative 7. Now, nobody would do this, but because now we were able to do that because of the linearity of t. Now we're going to evaluate the Laplace transform of 4t minus 7. We're going to use the linearity of the transform. So this is equal to the Laplace transform of 4t plus, let's make that a minus, the Laplace transform of 7. You wouldn't normally do it this way, but I'm just showing you how this works, the linearity properties here. Then, because I have 4t inside the Laplace transform and that transform is linear, we can say it's 4 times the Laplace transform of t minus, again, the Laplace, well, I guess it's minus 7 times the Laplace transform of 1, getting it down to what we've already computed. Since the Laplace transform of t is 1 over s squared, and the Laplace transform of 1 is 1 over s, this whole result is 4 over s squared minus 7 over s. And generally speaking, you're going to say, oh, 4t, that transforms to 4 over s squared. Negative 7, that transforms to 7 over s. And I know you don't know why we care about these transforms, but just stick with me. We're going to use them to solve differential equations eventually.